In this video, we'll be going over the process of setting up the pulse width for your myCNC controller. And this typically comes up when you're first setting up your machine. So for example, you've connected everything, you have set up the motors, you've set up the controller, everything's hooked up, and you're trying to, let's say, jog one of the axes, as I'm doing right now. And you can see that the on-screen coordinates are moving, however, there's no actual movement on those motors. And the fact that the on-screen coordinates are moving does mean that the controller is properly connected to your computer. However, when the controller is sending the signals over to the machine, something is happening. So typically the solution to that issue is to check the pulse width, or the width of the signals that your controller is sending over to your machine. And the issue here is twofold. So those signals can either be too narrow, so they're not wide enough, and if they're not wide enough, then they're effectively appearing and disappearing too quickly, so to speak, and the controller can't actually see them. Or they may be too wide, and in that situation the signals will overlap, so your pulses will conflict with one another, and you won't actually have meaningful signals sent to it. You will instead have a bunch of overlapping signals. And this necessary pulse width will be different depending on which motor type and motor brand you're using. So, for example, here I have a manual for a Panasonic. This is a myCNC A5 series AC servo motor and driver, and it's just a screenshot from their manual. And here you can see this T1 value. So for example, for the value of 4 megapackets per second here, I have the T1 of 0.25, so the actual period here will be 0.5 microseconds, etc., etc. So you have a number of necessary time widths, is what they call them. Next we have another servo motor, so this is the Yaskawa, and this is the E7 series. Again, a servo drive, and it also imposes a similar constraints on your minimum widths. So you have your tau in your graph, which corresponds to the width of the impulse itself, and you have your t, which corresponds to the actual period of the signal. So, and here you have an advice of having a t, or the width of the signal, ranging from 0.125 microseconds to 0.5 microseconds. So they are both for Panasonic and Yaskawa. They're specifying some sort of a minimum pulse width. And this is not limited, again, to servo motors. For example, I have this lead shine motor here. They're also specifying some sort of a value for your pulse width. However, typically your value for the minimum pulse width will be considerably higher on your step motors rather than on servo motors. So here, in this case, you have a value that's anywhere from 10 to 20 times higher when you're comparing the specs for this lead shine motor versus the Yaskawa. Okay, so as you can see, we have a different range of different pulse widths, and it's not actually possible for you to just have one pre-configured pulse width that will work for every configuration out there. So what you have to do, once you have set up your machine, you know your motors that you're using, you know the machine hardware, you have to calculate the necessary pulse width. And once you're done that, you can go into your settings, configuration, common hardware settings, and input the pulse width right here. So why the three values here? Well, This is different depending on the controller you're using. So for the ET6 and ET7 controllers, you would be using these first two values. So the first 4 motor outputs here and the next 2 here. Then if you're using an ET10, all the channels would simply be using this first value, so on an ET10 you would completely disregard these two. They can have whatever you want, typically 0. And on an ET15 you would have your first 4 motor outputs on your first value, the next 2 here, and the next 2 here. So now let's go over the process of actually calculating your pulse width for a sample size, or a sample calculation rather. Alright, so now let's try and go through the sample process to arrive at some sort of a suitable pulse width for our hypothetical machine that we're setting up. So first we have to choose a speed at which our machine will be moving. So this is our step 1. And our machine is moving at some sort of a speed, which is expressed in meters per minute, typically. Next, we have to convert the speed of meters per minute over to some sort of a value of revolutions per second of our belt or our screw, whatever is moving the system. And this is based on the value of meters per revolution of, let's say, that belt, and it's specific to your hardware setup. So we're going from here to here using this value. Okay, so now let's say that our desired speed is equal to 5 meters per minute. This sounds like a realistic speed for our machine. And our hardware value for meters per revolution is equal to 5 millimeters per revolution. So this is a pretty easy conversion to arrive at our revolutions per second. We go and do 5 meters per minute over 60 seconds per minute and multiply it by 1000 millimeters per meter, which is approximately equal to 80 millimeters per second. So this is just me converting meters per minute into millimeters per second. Next we take that 80 millimeters per second and we divide it by our value of 5 millimeters per revolution, and we arrive at 16 revolutions per second. So this is the value that we've been looking for here. So that's equal to 16 revolutions per second. Okay, now we're on to step number 2. We take this revolutions per second value that we've just arrived at, and we take a minimum allowed seconds per step value of the motor. So seconds per step. And we need to calculate from that how many steps per revolution the, let's say, stepper driver will have to make. So let's say for our example we have a minimum allowable value for the motor as being equal to 8 microseconds per step. So that's our minimum time that it takes for the motor to process each individual impulse. So this is 8 microseconds per step. And then we go and do our calculation. Just quickly delineate this. So it will be 1 over 16 revolutions per second that we obtained in step 1, multiplied by our 8 times 10 to the negative 6 seconds per step. So 8 times 10 to the negative 6 seconds is obviously 8 microseconds. And that's equal to 78, 12.5 steps per revolution. So the value of steps per revolution is equal to 7,812.5 steps per revolution. Okay, so as we've discussed earlier, the value selected must be equal or smaller than this number of steps per revolution obtained from the previous 2 steps for the motor to register the signal and to function properly. So, for example, if the value of steps per revolution has been calculated to be 7,800 steps per revolution, then let's say if the stepper driver allows for values of 3,200, 6,400, and 12,800 steps per revolution. So let's say it allows for 3200, 6400, and then 12,800. Then we have to select the 6,400 value of steps per revolution, as that's the closest value that's equal to or lower than this 7,800 value. So we will continue moving forward with 6,400 steps per revolution. Okay, and now we have to use, in step number 3, some sort of a revolutions per second value, and the updated stepper driver steps per revolution value we have to calculate from that an actual seconds per step value of the motor. And this actual seconds per step value will always be equal or higher than the minimum allowable seconds per step value of the motor, due to us selecting this lower or equal value of steps per revolution in previous steps. So this one right here. Now let's go through that calculation. We take 1 over 16 revolutions per second times 6,400 rather steps per revolution, and that's equal to 9.76 times 10 to the negative 6 seconds per step, which is also equal to 9.76 microseconds per step. And this right here in step 3 will be the value for our pulse width. So the value of pulse width in myCNC software must be set to be equal to or higher than this. And we'll be jumping back into the myCNC software to actually take a look at how we would do that in our next step. Alright, so now let's say we did find this value that we're looking for. So for us it's 9.76 in this scenario. We can use this chart right here to find which of these settings values, so from 0 to 7, we'll be inputting into the pulse width field right here. So let's say we found 9.76 microseconds per step, and the rule of thumb with this chart is that you are taking that value, you're choosing which controller you're using, so let's say we're using an ET7 right here. We're finding that line, and we're choosing the next bigger value. So let's say we have 9.76 somewhere here, the next bigger value is 12. Let's say we had the value of 5.5, so the next bigger value would be 8. Let's say we had a value of 2.1 microseconds per step, the next bigger value would be 4. So we choose that bigger value and we look at the corresponding setting value. So for 976, the next bigger value is 12, and that setting is 7 right here. So our setting value will be 7 and 7. Once again, if we are using an ET7 controller, we'll be using both of these values. For an ET10, it would be simply this, and for an ET15, it would be all three, depending on which motor outputs you're using and how many motors you have. Okay, so now that we found the setting value, we can save our configuration and our pulse width setup would be complete. At this point, when you're moving the machine, you're expecting some movement. Thank you for watching. Please visit our documentation at docs.pvautomation.com for more information.